Hello, good day, everyone. Good morning, good afternoon, good night, wherever you may be. Let's see. I need to switch off my sound as usual. There we go. I am trying a few new options today. There will be some attempts at zooming into things, and hopefully it's going to make sense. The work today. Actually, I need to change the prompt on the screen. We're not directly going to look at CockroachDB immediately. Instead, today is going to be a preparation for a conference talk that is going to happen later this week. I think the conference is going to be called Go Systems. All systems go. This conference, I think. No, that's not this one. Some conference in San Francisco. And I will be talking during that conference about this topic, which is the performance difference between using exceptions and return values for error reporting in Go. And this research was performed a while ago in 2018. And back in the day, the current version of the Go compiler was 1.13. The 1.14 had just been released. And now we're a bit further. And the current version is 1.15. And it is therefore necessary to verify the results that were obtained in that research back then before I can say anything about them meaningfully at the conference. And so the work we are going to do today is to revisit that work from back in the days and check experimentally whether the findings are still actual. And this will have another purpose, which is to refresh my own memory of the topic, so that I get some feeling again for the different statements that were made. And I also think that it's kind of nice to spend some time recording the findings on this topic again, so that later it's possible to refer to the recording on video for making a story about the findings. So, little background for this research is I like compilers. I like looking at code generations in compilers. I also like to look at how languages do calling conventions, which is a very low-level way for function calls to occur when they're translated from source code to machine code. And the interesting aspect here that's really worth experimenting is that the Go compiler does things in a way that is very different from other languages. And therefore, it's worth understanding what it does. So, we are going to do this with a test project. So let's go and do that. Do I have by any chance already somewhere in that list of projects a previous version of those tests? I might, but I don't remember. Let's see. Oh, I think there was a project called Callbench. That sounds about right. And there are a couple of files in this project, and I might hope that some of the files of the experiments from back then have been reproduced here. Oh, that might actually auto-generated return test. All right, so we have a bunch of functions here with different numbers of return values, and there is here a bunch of functions with different numbers of arguments. I'm missing one that doesn't return any value, but we're going to get there in a second. And so we're going to start with looking at the simple case before we go to this simple. Okay, so let's do this. So I'm going to kill those. So I have a bunch of things from CocoaDB. Let's exit all this. Right. So if I have a package and I do this, I'm missing this, and then I need a go no inline here, otherwise the compiler will inline the call. And now I want to compile this. Go tool compile simple.go. And what does this give us? No, it doesn't give us much. Compile minus capital S, I think. Yeah, here we go. So we're going to look at assembly code, generated assembly code. So empty func ret. This is indeed what is being reported. So what we see here in this output is assembly code generated by the Go compiler. The entries correspond to functions or global variables, global scope variables. And each function has a couple of directives that are not exactly machine code, like text, for example, and func data. These are metadata for the linker and the call stack gathering function in the Go runtime. And then we have the actual instructions. So what we see here is that this particular simple function has just a single machine code instruction. If we were to replace this, or sorry, add this function here, let's see, I hope it doesn't get elided during the, there we go. So func const, the one we just added, moves value to some position in memory and then returns. So that's what we see here. So already there is a, let's ignore for a second the fact that the style sheet is kind of broken on my website. I don't know how to fix that, and we should not care about this. But the assembly syntax between the time where I did this research for the first time and today, the assembly syntax has changed. So it's not so clear to me yet what dot tilde R0 plus something means, but my intuition would be that we are looking here at a relocation offset. That means that back in the days, it's possible the code was not being relocatable by default, and now it's being made relocatable by the compiler, and that's what this offset we're seeing here is what this is about. I think I can ignore relocation entries, but it is a case that because the output of the disassembler has changed, it's going to be valuable to bring these findings in the article up to date to update the assembly that is pasted in the article for example purposes. And so I'm going to start making a list of notes of things that need to be updated. So okay, so that's an old to-do list. Let's do a new one. So assembly examples have changed syntax. It's kind of sad that this article does not use automatic generation for the examples. So let's go there. So this is going to be func const like this. Let's continue. Then we are going to use, to go a bit further. So the go no inline directive is a non-documented internal directive for the Go compiler. Its purpose is to disable function inlining. Regular applications typically have zero reason to use this. This kind of directive exists for two reasons. One is that certain functions inside the Go runtime itself can only work if they are not inlined. And the other reason would be, for the kind of experiment we're running out today, is to understand what the Go compiler does. So what do we see here? func_add, we see that it loads two arguments from the stack. Oh, here, I think I understand. So this is not a relocation entry. I think these are pseudo labels that look like relocation offsets, but they are giving me, as a reader of the disassembly source code, some information about which are the variables that are being loaded from the memory. So it's a reading aid. It's not actually a relocation entry. So this is going to load the two arguments, then they're added together, and then the result of the sum is stored into the z variable. And then there is something happening here. Oh, it's because my function is actually doing a plus b minus c, right? Yes, right. Okay, so it's loading the z variable into 6 and then subtracts it. And then the result is stored into memory. So that's absolutely worth pasting here too, so that later on I can update the example. And so in the first example, we had a tilde r0 is because the variable in the function did not have any name, so the compiler created an internal temporary variable name for us. All right. So we see that the original version of the code was more or less using the same logic. So the update is still generally valid. And then we are going to continue verifying this. So here we see a simple call. So here we were looking at the way the function pulls its argument values from the stack. And now here we want to see how the compiler pushes arguments into the stack. All right. So this is our function. So it's kind of longer, and there are multiple things happening here, including a few things that I believe were not being reported earlier. So this is an example from the previous example back in the days, and so there is an explanation in the article that says, well, we can focus on what interests us, and that is just this. These 4 instructions move 3 values into the stack at the particular position that the function is expecting them from, and then at the end it extracts the value from the stack where the function put it as a return value back into a register. So that's like the meat of the code. And in the new implementation here, we actually see the same logic is still there. But now we see this PC data and other things. I think actually I don't really like, I actually don't really like anymore this Go build. I don't like using Go tool. I prefer to do the other mechanism, because we're looking here at the input of the assembler, and it's containing all these directives, and what we really need is go tool ob dump. That gives us more noise, but we are actually going to get more compact output. There we go. So that's actually more pleasant to read. So, okay, well, maybe that explains the findings from before. So it's not the case that as I had thought that the assembly language has changed. It's more that we're looking at the direct compiler output before it would be input to the Go assembler. And that means that a lot of these directives here that are meant to aid the reading by the developer reading as assembly is being stripped out during the actual assembly step. And that is probably what we need to look at instead. And that is the result after assembly when we look at the disassembled code. And that is much closer to the original example. So I suspect that these examples here were pulled from the disassembler. And so maybe we're going to continue doing that because that makes it easier to detect whether there are differences. So let's see. So we have this code here, and as we explained, we have those instructions here correspond to the main function call in the source code here. And then now we want to understand what's going on with the rest. So there is a test here, which is about increasing the stack if it's not large enough. So what's happening here is that if the stack pointer is pointing out to locations that's too close to the end of the reserved area, then the program is going to jump back here. And then here it's going to call more stack, which is a runtime function to increase the stack size, and then it will come back here to continue the processing. So what do we see here? There is a subqueue to create some space on the stack for passing the arguments. Then we save the previous base pointer for frame unwinding in case the called function panics. And then we set the new base pointer to the current frame. And then we have our main call sequence. And then the result is stored at some location on the stack. And then the frame pointer is unwound to its original position. So that's actually probably very close to what we had originally. So we see here in the original program the same instructions, and then the same call and the same restore. So all in all, this example really hasn't changed. And so there is some explanation written in the article, which is more or less what I just explained. And now we are going to look at the so that's an aside about C++. We're going to look back into Go here. All right. So what we want is to verify the understanding we got by measuring the size of the arguments as passed on the stack. All right. What's happening here is that we need to actually have calls to the functions we want to inspect in the main program, because otherwise the Go compiler in its generous benevolence is removing the functions we're not using in the code. So use PTR. Use PTR takes a pointer as argument, different references, and returns the results. So we take the argument into the register by pulling it from memory. Then we dereference it without an offset. That gives us memory, the location at the memory pointed to by the pointer, and then we take that value and store it back as a return value. So that probably hasn't changed since last time. It hasn't. And then the other two functions are here. So this one takes the value of the global variable table and loads it. Then we store it. So that is a confirmation of the assertion made in the article that a pointer in Go has a single word of size. If we have an interface type, then we are going to see that the interfaces use 2 words. What's the name of the thing again? soar PS, move UPS. I was not aware of this instruction, but as we can find out by reading the Go assembler sources, the X registers are actually XMM registers in x86, and so we see here that this move is taking the entire 128-bit register and moving, setting it to 0 and then moving on the stack. So we are talking here about a double word memory move. And so I'm not expecting any surprises here, since we already asserted the sizes, and just moving the data in and out of a function is going to cost the same price as before. So there is no reason to reproduce this experiment. And now we're going to verify the strings and the interface is actually documented to have 2 and 3 words respectively. And therefore, we don't really need to test this. This is part of the actual Go documentation. And now we're going to look at the vtables. So let's verify that this code still behaves as it originally did. Okay, so I don't want this X anymore. I don't need this functions from the beginning. Then our interface has changed, and now we are going to try it out. So what do we see? This instruction loads the address of the visual table for the foo type into, that is Go weirdness. So this is the implementation of the foo interface as of the struct called foo with a small letter. And that is then stored in the registers, that is stored in memory. And then we have the address of the global variable X, and it's stored in the next word in memory. So we have here a 2-word result, one for the visual table and one for the address of the object. So that is a confirmation of what has been stated here. We have the same result as before. Then we can verify what happens if we implement an interface by value. What we're expecting here, when an interface is defined by value, what happens is that the Go compiler has to generate a move of the variable into the heap. We're now going to verify this. Come on. Oh, I did not mark it as no inline, so the compiler helpfully removed the implementation. So let's try again. All right, so what's going on here? We have here our prologue, because we call some functions below. So we need to have this prologue that is going to verify whether the stack is large enough. And then we go to a check here, which is about increasing the stack frame for the current function and setting the base pointer for the frame pointer for it. And then we have the meat of the program. So this loads the variable y by value into this register, stores it into memory, and then converts it. And what we are doing here is that the value is converted to something that can have a interface vtable next to it that basically moves it to the heap. And then the vtable address is stored into the return value of the function make interface alongside with a pointer to the value that has been copied to the heap. So I think that the result is the same as we had here. So before, the code was loading the interface and storing into memory, and only after that converting the value to the heap. And what we see is that in this new code, we have a different order. So it's getting converted to the heap, and then only the interface pointer is loaded. So, okay, so now we have a real case of an example that has changed. So the ordering of the operations in the generated code has changed, but more or less the same. So what is explained here is that, well, what we just explained, this is moving the value into the heap and getting its pointer. All right, so continuing, interfaces to empty structs, in which case the interface can be implemented value without copying the value to the heap, because all the struct types have a singleton in memory. Yeah, so I don't want X anymore. Where's X? Where's X? So this goes away. Make it over 3. Because we have now a singleton, we just load the interface pointer. Then there is a general purpose empty struct 0 base that we can use, and that implements the interface. I had hoped or expected perhaps that the empty struct would have a different instance per type, and this seems to be the same empty struct base for all the types. Maybe, I don't know. Oh yes, yeah, here we see. Okay, so this is the, that's what we see here. All right, so our empty struct type is called empty. That's what the type def here is defining. And so what we see is that this type has implemented the full interface, and it has its own method pointer. And so this entire interface virtual table contains exactly the implementation by that type. So if we had another struct type with a different name, then we would have a different interface vtable to load. All right, so this has not changed. Now, error is an interface type, and therefore, if I have an error return and I return nil, I'm going to expect this nil in the body of the function to be converted into a double word, one for the error vtable and one for the 0 byte of the nil reference. So let's check this. Yeah, it does return 2 values indeed. All right. So what we see here indeed is that the oh, that is odd. Oh, interesting. Okay, I don't fully understand. Oh yeah, sorry. Oh, my apologies. This function has 2 return values. That's what we're seeing here. So the first return value is 123, and so that is what is getting written here. And then the second value is nil, and so we see a double word 128 bits that value being set for the nil return moved also to memory. So it's the same function here. And then if an error has been pre-allocated, then it's going to get extracted from the global memory and then written to the stack at the location of the return value. So let's verify this. Oh, hi. I see the question, what is the project? So the project is the following. We have a conference talk happening later this week where the topic will be to how the use of exceptions in Go is going to yield better performance in some cases than using return values for errors. And in order to make those statements with a lot of confidence, it's pretty much necessary to verify experimentally that the results that were obtained in 2018 with Go 1.13 still hold with the new version, which is Go 1.15. So if you want to follow along, how can I do this? I'm going to take this URL and I'm going to paste it into my Tmax configuration in the status lane. I think we are going to do this like this. And then this. Right? Yeah. So now you see the URL of what we're currently checking as the bottom right of the screen. So in particular, what we're doing is verifying whether the generated code by the Go compiler is doing what we expect it to do, that we don't get surprises, and that the explanation that was written earlier for 1.13 still holds in 1.15, and if there are changes, that the changes are minor. So what do we see for this function compute? We have a function that says, well, if the divisor is 0, then we have an error return, otherwise we have the result of dividing. So let's try to recognize this code here. So we load the argument from the stack into x0. That is a pair of values. So xmm is a 128-bit register, and we have two 64 bits. So I'm kind of expecting that this is loading two of them. And then this is erasing entirely x1, and then is copying the first word, or maybe the second word, I don't remember which of the two instructions, into x1, and then we have those conditionals. And so what it does is that if the value of the divisor is not 0, then it goes to this address, and this address is here, and that will do the division, and then the division will be stored before the function returns. Otherwise we have this error by division by 0. So this gets loaded into two registers, and then there is the value from 0 gets stored into here. Oh, so x1 was set here to 0. So this stores 0 as the first return value, and then the two words of the error object gets returned as two different places in the return values, because the error object is composed of a pointer to the error object plus the interface for the error type. So I suppose that the explanation from back then hasn't changed much. Yeah, the instructions are the same as earlier. So this has not changed. And then we have this function here that is not anymore using a global error object, but instead is constructing the error object from scratch. And that is going to give us more complexity. And so the complexity that is happening in this case is because this function is not just returning some value with an interface type, it's also going to call another function. This errorf function from the format package is a variable argument, has a variable argument list, and so there needs to be an allocation for a slice to put the arguments in. And so it's going to be more generally a more complex calling convention. So let's see what we see here. Yeah, so indeed there is more code going on here. So it's possible to go and analyze this bit by bit to the explanation, but I don't want to make this a stream about re-explaining the same results. So we're going to verify simply that the explanation is more or less still the same as it was back then. So we have the stack check. The entire initialization here is supposed to be just setting up the stack. Oh, actually, the shape of the function is different from it was originally. So it is possible that the experiment here needs to be revisited. So I'm going to recant on my idea to not look at the general assembly and go here actually at the code. All right. So what we see here is a call to the RF function. This is moving a temporary allocated slice into the heap, and then at the argument position for the RF function, and then calling the RF function to construct an object. Well, so in fact, this is actually more or less what we saw the previous time. I do need to make a note in the file where we are keeping our notes that the function has changed shape. So second compute function with ft.rf. So the specifics have changed, but the overall structure is still the same. And then we have those cases where we have a check for a nil error in a function. So the precise contents of the callee function doesn't matter because our callee function doesn't get in line, so it's not going to pollute the code of the caller function, and the caller function is what we want to inspect here. Caller. Come on. I'm not being lucky. Main.caller. All right. All right, so what we want to see is that after the callee function returns, we want to see how this this error reference check looks like. So the function gets called here, and then we see the value of the error gets loaded into this register, and then we have a test, and if the reference is nil, then the jump is performed, and that jump goes to 55, which is here. And so what it does, it returns -1. And so this is a call. And so it says return -1 plus cx. And so cx must have been initialized somewhere before. Yeah. So cx was initialized as -2. And so -2 plus 1 is going to be -1, and that gets stored as a return value. So that's what it does. So why does this compute -1 as -2 plus 1? I don't know, but it doesn't matter too much. We're happy about that. So it is the case, though, that the common case, so this example looks very different in this version of the compilers than it used to back in the days, Windows 13. So again, we're going to have a note that we need to upgrade the assembly example here. So is it qualitatively different? Not really. The test for the error is still test queue followed by GAE. That is still the same today. So that test for the nil error has not changed. And then we're going to look at defer. So defer, I am already certain, has changed a lot. And the reason is that this was an announcement made in the release notes for Go 1.14. Was it 1.15? I don't remember. That the defer implementation has been rehauled so that it becomes much cheaper. So what does much cheaper mean? We need to figure that out today. So what does defer1 do at a low level? This is going to be a bit more exciting. So we don't know exactly, and we need to figure that out bit by bit. So the way to do this is to take this code and actually maybe make it on 2 lines so that we have a bit more information. Here we go. So now we're going to copy this into the text editor. Like this. And we are going to eliminate the opcode because that's super interesting. And we're going to look at what's going on here. So we have a defer call on line 8. So that's the function header on line 7, defer call on, defer definition on line 8, and then the return on line 9. And the disassembler is helping us by giving us the line number. So all that is on line 7 is related to the entry of the function. And so what we see here is something to do with allocating a bigger stack if it's not big enough, preparing a stack frame, setting up the return values for the function in case the defer gets called by panic before the value 1.123 is stored into the return value slot in the stack frame. And then we go at line 8. And that is where things become interesting because they are different. So this is going to be, say, defer call. We are copying some offset from the IP register. So IP is the current instruction. So this is an offset from this address. What this precisely does is unclear to me, but it is possible that it has to do with the defer return. And then the value of AX is being stored at some points, and we have another point, then 0. So these are markers that are going to be stored at a fixed location related to the stack pointer that are going to probably to inform the defer call whether the return value has been written already. And then the function gets called directly in the return path, and then the function returns. So what we see here is that the defer is not actually entering the go runtime in any point. Instead, it just copies the some offsets from the current instruction pointer into the location of the stack, and then it ignores it. So what we are seeing here is that because our function is not performing other function calls and doesn't perform any operations that are likely to trigger a panic, say the F call is performed in line, and there is no conditional anymore. There is no looking up the list of defers for that function and so on. So this is a case where the Go compiler is now much more clever than it used to be, because in the previous implementations, if I recall correctly, it would go to Go runtime to register the defer in some way. So we see here this code that was deferring the call, and it was a function call into the runtime function, and that has completely disappeared. The only thing that remains is this call runtime.defer return at the end, but that's kind of odd because this function is not going to be able to call this defer. Like, it has no operation that's going to create a problem. So in order to get rid of this optimization, I mean, not rid of it, but like in order to verify whether this optimization applies only if the compiler knows whether the defer is unconditional or not, we're going to have another function g that is going to be called unconditionally, so that the compiler doesn't know by looking So this no inline also prevents the compiler from peeking into the function to know what it does. And so this call here, actually I don't know that for sure. Let's make it so this way we make a function which the compiler doesn't know whether it's going to panic or not, because it doesn't know the value of x when the function defer1 is called. So G may or may not panic. So this defer now will going to cause f to be called on the return path or not. We'll see. Let's see what this does. All right. So this stores a pointer to our f function, and then it calls g, then calls f, and it returns. And so the this is really interesting. So what we see here is that instead of calling a function in the runtime system, the address of the deferred call is being stored into a location on the stack. And I think that when the panic unwind is occurring, it's going to look at this and directly go and call, for example, this part of the code. That is very interesting. So here we have a case of a defer that calls a very simple function. What if I had multiple defers? Okay, wait. Yes. All right, that's more interesting. Oh, that is beautiful. That is definitely worth going to create. I'm going to create an amendment in the article. So what we see here is fascinating. We see the offset is being stored in this register, so it's likely to be the offset of the function f, or a call to the function f. And that is then copied to multiple places on the stack. And then next to this, at the offset 7 from the stack pointer, each time we add an additional defer, there is a byte that is being updated on the stack at that location. And so what I understand from this is that this byte is informing the unwind logic. How many defer pointers are there on the stack at that time? So the unwind logic will go and look at this location on the stack, read how many things to do, and then do them one by one, and it's going to pull the arguments from the stack pointer at the various offsets from that location. So why we see 1, 3, 7, whereas we just have actually 4 defers, it's going to be, we would need to look at the source code of the runtime to be sure, but I believe this is a flag plus the number of defers shifted by 1 bit to the left. So this is telling us there is a defer at that location and there is just 1 defer. And this is the value of 1, then a flag 1 OR with a logical bitwise OR. And so this is telling the Go runtime there are 2 defers. This is a value 3, shifted by 1 plus 1. And that gives us 7 in total. So that tells the Go runtime there are 4 defers. Something like this. Okay, I will admit a little bit of ignorance. Either it's that or the number of bits set in the byte is the number of defers. Oh, number of bits set, that is cool. So that means we might have an optimization for 4 defers, and the moment we have sufficient number of them, it has to switch to a different logic. Let's see what it does. There we go. Okay, that is so cool. Okay, that is really cool. So what's going on here, what we discover here is that there is an optimization in the generated code. So there is a byte at a specific location where the number of bits indicates how many defers are to be found on the stack frame directly. And as long as we have 8 or less defers, it's going to use this mechanism that is byte-based. And so in this particular case, we have 8 of them. So it's going to set all the bits to 1 to say that we have 8 differs. And the moment we have one more, then this mechanism with this byte doesn't apply anymore, because we can store more than 8 bits set to 1 in 1 byte. And so it has to switch to the more expensive mechanism that is documented in the article. So what we see here is that in the case where there are 8 or less differs in the code, the setting up of the differ on the call frame is cheap. It's just storing 1 byte in a fixed location and then a pointer at some place in the stack frame. And the moment we have one more, then all the differs starting from the first become expensive. That is so cool. That is very different. So we are going to call about the differs logics. So optimization with 8 or less differs in the function. Say setup of the differ calls just stores one word to the closure, I assume needs to be verified, in the stack frame, plus sets 1 bit in a byte at a fixed offset from SP example. Then we're going to take this example from earlier. Example. Like this. And so with 9 or more differs, the old slow logic is used instead. That is going to be valuable for the endpoint of the article. It's actually going to strengthen the argument that's going to be presented during the conference. We're going to see that about that later. Deferred closures. So now here we're going to have a simple case because we are going to enable this optimization. So what do we see here? The mechanism from earlier is probably going to be preserved, so that we're going to have just one byte set. But this time we have a little more complexity because our closure is referring to a return value by address. And so it needs to escape this. And so we need to save the address on the stack to something else. So let's see. So this is where our function starts. So this takes the address of the closure and then stores it at this location. And then it takes the argument position, which is the ret variable, and stores it also on the stack somewhere. And then it stores the value 1 on this location related to SP. So that is the location where of the defer byte that with all the bits set. And then it finishes. And then it calls the defer call. So it does set up the defer, but it doesn't see that the return is unconditional. So the defer is actually set up even though it's not going to be called. That's okay. So it is simple. It's also cheap. Let's see what the article was saying about this. So this is of yours very much more complex because we had that defer proc call due to the optimization not being present back then. But nevertheless, say the closure is going to be the same mechanism. We store the address of the closure, and then in the function in the closure here we have this movq. So let's see if the func1 is there. This is our func1. So it takes the argument the res variable, and then it sets it to 123. So all these mechanisms that I explained here is more or less applicable modulo this new optimization in 1.14 and 1.15. So that's kind of cool. Now we're going to look at the panics. What is the calling convention for panic calls? Before we do this though, it's been 1 hour that we have started this stream. And so it's never good to stay at the same chair for more than 1 hour. And so it is time for a little stretching exercise. So I will be back in a few minutes, let's say 5 past, half past, so 35 at the latest. See you in a bit. And we are back. Let's resume. So the next step is to look at the shape of a panic call in Go. So what does a panic call in Go look like? We're going to have to call those two functions explicitly. So panic 1 contains first a stack alignment, stack growth check. Then we have the regular setting up the frame pointer, and then a value is set to 0. So this is a panic with a double word, nil. So panic takes an interface, an empty interface argument. So it's an interface type. That means that we have 2 words. So it's set both to 0, and then the go panic call is made. So this is a regular call. And the other case, we are going to pull out a global variable and panic with its address. So same story as earlier. The stack frame is being set. Then we have here a X variable is being loaded from related IP source relocation, and then stored on the stack. Then the address is stored on the stack. So, oh, interesting. So there's something going on here. This I don't understand. Move BP. Oh, this is setting up this frame pointer again. Okay, so that's setting up the frame pointer. Now we have this here. So this is setting up a closure, an address of the code into the value 0 at the stack pointer. So what does this do? I'm not sure. Let's see if the previous article had something to say about this. So this case here, does it look similar? Yeah. So we have actually something that is very close to what we had before. So we can ask the explanation here what it says. Oh, it's a virtual table for the empty interface. All right. So indeed, okay, so panic needs to have 2 words of arguments. So this is setting up 2 words of arguments. This is the address of the variable, and this is the address of the empty interface vtable. So this has not changed. We are still looking at the same things. And now we're going to catch exceptions with defer and recover. So what can we expect from this kind of code? So for context, what is written here in the explanation, the pseudo function recover returns nil when you call it by default, but then if it is called in a context of a panic, especially in a deferred function, then it's going to return the panic object instead and stop the propagation of the panic object. And then it's not really a function. It's actually a mapping to a special function inside the Go runtime. And then we have the defer here. So what we saw in our previous experiments, that differs when there are 8 or less of them in one function, is going to be a simpler implementation. So this recovering of the this recovering call is going to be simple, to have a simple setup in this try-catch function. But what interests us in this experiment is whether the recover call here has changed shape. So let's try this out. Missing return at end of function. Which of the functions is missing return? Here. So what we expect here is that the recovering function, the try catch function below here is going to be simple. So what we expect here is a defer as we found how it was done before, a call to f, and then setting up as a return value. So how does that look like? We have the regular setting up of the stack frame here. Then we set, there is a nil value being set as a return value for the function. So the result variable here starts at 0. And it lives at the offset 10 in hex from the top of the stack pointer. Then, this is a special address that marks the number of differ, starts at 0. Then we get here some variable set on the stack, address of the closure for our differ, moved into some location of the stack, and then the address of our argument, which is the variable for the return value, the rest variable, and then we have here our differ call is registered by writing the special byte, followed by the f call, followed by the recovering call, and this is valid because it's deferred, so it has to be called, then return. So all this is exactly what we expected for the try-catch function, and that hasn't really changed since the previous version of the compiler. This code, this explanation is not even looking at the try-catch because there is really no surprise in it. What's interesting more is here. So what does this recovering call do? We are going to look here at a call to more stack if the stack pointer is to, if there's not enough stack left. Then we have frame pointer being set up as usual. And what we see here, we get a recover call. So what this does, it stores the address of the return value into AX, and then it verifies the return value stored at this location from the recover call. So really, we still have a recover function in the runtime function called as usual. So that has not really changed. We see the same code that was performed before. So defer and recover function more or less the same as it did in the previous version. What changes is the registering of the defer calls in the function that contains the defer keyword. But the execution of the deferred function is the same. It's a regular function call, and the recover call is handled as a call to a function inside the Go runtime. So there is no magic happening here. And so if we look at the cost of this combination here, we have a cost that is, as before, setting up an activation record, setting up the deferred call, and performing the deferred call on every return path. So this is where there has been some saving from the previous versions of Go. So defer and recover are costly because it needs some stack space. It needs to set up the defer call. In the previous version, that was performed by making a call to the Go runtime to this function called register defer or something like this. And that call has disappeared for most cases where there are 8 or less defer keywords in the function. Or when the compiler can prove there are 8 or less. If there was a defer in a loop, for example, the situation would be different. And so the idea is more or less the same. Just some of these costs are lower. So this article here needs an update to mention that there is no optimization, but the general gist of the conclusion has not changed. And now there is this question that is going to be answered much later. And what is the cheaper? Do we panic or do we check return values? And so there is some explanation here that depending on whether you have a lift function or an intermediate function, it's going to be cheaper or more expensive. So all these conclusions need to be checked later on based on the new learnings we made today. And then there is some analysis of GCC Go. And here there is something that we could be doing, and that is to reevaluate the findings with GCC Go and see if anything has changed. But the truth is, this entire section of that article in 2019 was garbage. There was a methodological mistake. The GCGO invocations were incorrect. And so all the findings here were found without optimizations, which is unfair because the Go compiler enables optimizations by default. So all these findings in this section here should just be ignored. And since the experiment originally was incorrect, then it doesn't really make sense to try to compare today's result with the previous results, because the previous results were not worth investigating. So we're going to skip this section. And so there is a summary here. So in terms of the examples and the findings, we have more or less similar findings. And now we're going to switch off to the next chapter, which is a cost in performance of returning multiple return values. So what we found in the analysis today is that the setup of the stack frames and the general behavior of conversions between pointers, interface, and so on is more or less the same today as it was. The only thing that has really changed is defer. And so what we're expecting is that this entire this entire document here is going to be more or less reflecting the same results today as it used back then. And so there is a comparison going on with C++. Is there any of these experiments that needs to be changed? No, but there is an automation. There exists an optimization. So let's see. Oh. It says that it doesn't have a rule to build this. Why is that the case? Bench.h not found. It is here. Oh, yeah. Probably because it needs to have an include path. And now this is going to run, say, C++ example. I wonder, is this a single core application? So probably this does not get too much interference if we were to run other experiments at the same time. Is that the case? I'm not expecting too much changes with the original C++ version. Let's go and verify the results from last time from GitHub. If the results are more or less the same as we see now, then we should not even spend too much time looking into it. So what do we see? We go 136 nanoseconds, 163, 165. So the computer I'm using now seems to be slightly faster. So if we have 8 values, we have here 2.44, 8 values here, 2.48 originally. So yeah, I'm using a different computer from back then, but generally we get some additional, little bit of additional performance by a factor of, let's see, 275 compared to 271. So let's see how much that would be. So we are 2%, 1.5% faster now than we used to. All right, I'm going to cut this experiment short because what we really want to see is the result of compiling the Go example. So let's see. So this is now running the same tests, the same logic with the Go compiler. And let's see what the results were back then with the Go compiler, probably 1.13. All right. So back then we had a starting point for one return value at 254, and now it's 1.63. This is actually very significantly faster back then than it is today. Sorry, it is faster today than it is back then. And then if we have a multiple return value, then we are now back again in the same benchmark, ballpark as earlier. Let's see what it says for 8 return values. So we were at 3.32 nanoseconds, and now we're to 3.25, 3.87 for multiple, and 3.80. So let's go there. Let's see what it says. 3.80 divided by 3.87. So we are 1.8% faster. It's actually more or less the same improvement that is probably going to be due to architectural improvements. And so I am of the opinion here that the performance result for the return values in the article has more or less been preserved. Of course, for correctness, it is necessary to run this experiment until completion, but I estimate myself satisfied right now that results are congruent with the findings previously. And then it's going to be necessary to update those diagrams here with a new version. So we have up-to-date figures, but I'm more or less expecting the same results. And then we have these intermediate calls. And all this is a Python notebook. So probably we can rerun this notebook by just loading it into IPython or Jupyter and rerunning all the diagram generation. So I'm going to do this off camera. Then we have this other experiment that is benchmarking not return values, but argument passing instead. And then we're going to compare in Go how much improvements we have from back then. All right, so arg0, 280 picoseconds per operation. So it's very close. We're in the same ballpark. So if we have 8 arguments, fixed argument list, 3.25 nanoseconds, and if it is a variable argument list, it's going to be 6.33 nanoseconds. Let's say here. So we were 364 and 808. So 364 down to 325. That is a nice improvement. How much is it of an improvement? It's much more than last time. This is actually something like 10% plus improvement. So we are seeing here benefits that are beyond architectural improvements probably. That is probably worth going to look at this generated assembly at some point, but that's okay. What we're going to do is just say, well, this is science, there are improvements, and we're going to quantify those by rerunning the IPython notebook. So passing the arguments here will get us some diagrams. And there will be some explanations. And what is really important now is to go back to the main findings, which is a comparison of the panic versus returns. And then there is a baseline, and there is a comparison. And so again, there will be a automation possible. Let's see. We need to, let's go. And now we're going to compare. it's going to give us the cost of exceptions, cost of errors every time. And so what we saw very clearly in the initial results from last time, if a function does not do any error handling, then its baseline is 2.99 nanoseconds. And if it has just a return value or just one panic object, then doing it with panics starts with 44 nanoseconds per operation, and with errors is 254. But at some point, there is an inflection point, and that has to do with the call death. And so that's where we're going to compare. How far were we in the difference? So there is a diagram here. This is probably, this is diagram that is interesting. Overhead, relative, and then the inflection point. Is there an inflection point somewhere? Yeah, it's here. I think that this experiment I'm just running right now is just the overhead measurement. Okay, let's come back here. So back then we had this mandatory call to the runtime function. This is called defer proc to register the defer. And so we saw today that this overhead has more or less disappeared. And that's actually pretty great news. That means that the overhead of setting up a panic, a defer to recover from a panic, is now much cheaper than it used to be. And so if we have, say, 50 values, then it's more or less equal costs, regardless of errors or panics. Interesting. The overhead is the same. And then 500 is converges. Cool. There was another experiment to run here, and that is when there's more work to perform per this one here. Oh, maybe that is the test that I'm running today. Yeah, that is what we're doing here. As the amount of work inside the function increases, the two converge together. That might actually be invalidating the finding from last time. Does it? Yeah, it does. What we saw last time is that there was an inflection point whereby as the amount of work inside the call tree increased, then it was more expensive to deal with panics and recover. So it was more expensive to deal with returns, error returns, than to do with panic recover. And so there was an inflection point at some point around here. And what we see in the new findings now is that the cost with panics is actually more or less the same in terms of performance. There is a very slight excess cost here, which probably needs to be investigated more, but it is within a couple of percent performance, and therefore the difference is really negligible. And so the article back then is going to be making a statement that the performance difference back then was so that there was a reason for doing panics more than errors that is just related to performance. And that argument here, without further analysis of the exact generated code by the compiler, might not be true anymore. That means that as time went, the Go compiler has become better at eliminating the difference between the two. So that's actually pretty interesting. So why is that the case? Well, that probably needs to be looking at the generated assembly code for the benchmark, and then based on that generated code, find out if that was like because of a specific case in the benchmark, is a specific way the code was written, or whether there is a more structural reason that is pervasive throughout the the generated codes that will offset completely the difference. So either the methodology here has a gap, and so the overall argument of the analysis last time remains, but the demonstration of it needs to be different, or the experiment is very representative of reality, and then the finding is different, but then we need to find an explanation of what has changed in the compiler to explain why the findings today are different from what they were back in the days. So, well, we are about time for today's stream, and that means that we won't be able to continue this analysis directly within the stream. However, it is a case that there is a question here that is absolutely non-trivial and is some further investigation, and it's absolutely demonstrations that reproducing the experiments from 2 days ago ahead of presenting the result at the conference was extremely important. Otherwise, the results and the finding presented at the conference would have been outdated and would not be reproducible by someone starting with today's tools. So, moral of the story, it was pretty important to do this. And I think that we learned something, both about the new mechanism used to register defer calls inside a function when there are 8 differs or less, and the fact that there is something that has changed in the calling convention, whereby there is no direct inflection point with the experiment that was run last time, 2018. And so we need to find out what has changed really, whether the Go compiler has become more clever, or whether the experiment has triggered some optimizations that we want to get rid of to find the same result as last time. So a little more investigation is needed. And once that is done, then I will update the article that was published last time and add a new chapter with the findings from this year, and then cross-reference the two with the new results, so that the conference has some more updated results to work with. So here we are. That was the findings for today. This summary and conclusion from last time are probably not correct anymore today and need to be altered. That is really today's conclusion. And that means that between now and later this week, this article is going to have a note here saying, well, this summary and conclusion are not actual anymore, and the reader is invited to go to this new article to show what the current results are instead. Thank you for watching. Thank you for accompanying this little scientific what is called expedition in the internals of the Go compiler, and hopefully you would have learned something about how to read generated Go assembly. And if you have any questions or any comments and so on, I will take them either on Twitch or on Twitter. Thank you for watching. Thank you for being there. See you later.